What's going on, everybody? My name is Johnny Bannon, and I'm the CEO and co-founder of Trepa Technologies. In today's video, we're going to be going over cryptographic protocols. So this is going to be domain 1.4 in our Security Plus SY0-701 video series. So this exam, or this subdomain 1.4 is pretty in-depth. I think I have 67 slides to go over, and it's all very complex topics. So when we dive into encryption, PKI, we dive into encryption tools like hashing, salting, digital signatures, secure enclaves. It's going to be a lot of information. So we're probably going to divide this video up into about 3, 4, maybe even 5 videos, just depending on how in-depth we go. And there's going to be some things that, for some of our cyber security professionals out there watching this course, because maybe you just have to get certified, one thing the Security Plus exam doesn't have in this section is ciphers. So there's going to be a bonus video that comes out after this full video course is done, because this video series just goes over the exam objectives. And yes, it talks about encryption without talking about stream and block ciphers, which, again, I don't think is good, but we're here to get you certified in CompTIA certification. So with that being said, let me go ahead and get my face out of the way and begin the lecture. Okay, let me hide my face. Awesome. So again, you can see here that we're going to be going over domain 1.4 cryptographic concepts or protocols or solutions, however you want to call it, right? We're going over cryptography right now. So as you can see, we have quite a few objectives here. So the first thing we're going to touch on is encryption. That's what this video is going to be about. And I'll probably get to about right here, okay? And then key length, I think I put in like over here with key stretching. I can't remember exactly. Then the next video is going to be going over PKI. And then we're going to go over PKI components. And then lastly, we're going to go over some cryptographic tools. So that's going to be things like TPM, hardware secure modules, key management systems, tokenization, things of that nature. All right, so the first thing we're going to touch on is, what is encryption? So encryption, this is the process of converting information or data into a code to prevent unauthorized access. A fancy way of saying that this is how we turn readable plain text into something called ciphertext. So plain text is just going to be exactly how you would read something. It's, hello, Jim, how are you? And that is plain text. When we apply an encryption algorithm, we convert that plain text into ciphertext. So as you can see here, encryption uses an algorithm and a key to transform readable data into non-readable data, or non-readable format known as ciphertext. The key piece of information, which is going to be a sequence of bits, right? Because this message right here is just all bits, is used by the algorithm to perform the encryption. So our encryption algorithm just has two main components. One is going to be the actual encryption algorithm here. This is an asymmetric encryption algorithm. And then, of course, the key. And then that key size is also going to determine how strong or how secure that encryption is. So think of encryption like a secure lockbox. You can put your message, your plain text, right, inside the box. The key to lock or unlock that box is the actual encryption key. And then once locked, now encrypted, the message is safe and is unreadable to anyone who doesn't have that key. So imagine again, we have this lockbox here. This is how I'll draw a lockbox, right? Little hole, that's where our key goes in. If I put my documents in there, so here's all my documents. If that key box is my encryption algorithm, right? It's meaningless without an actual key to lock it. That's where the encryption key comes in, okay? And during this section, we're going to go over two types of encryption. We're going to go over symmetric encryption, which uses a single key, and asymmetric encryption, which uses key pairs, and we designate those key pairs as public or private. So again, a real-world example of how we'd use encryption would be us protecting our data in transit. So using HTTP connections using TLS and cipher suite or encryption suite to protect our data in transit. We could protect our email traffic, ensuring confidentiality of our emails by using encryption. Okay, now let's move on. So that was just kind of the baseline of what encryption is. So again, why do we use it? So we're going to go over a couple key terms here. So we use encryption for the big one here is confidentiality. To ensure that sensitive information, whether that be personal data, financial information, confidential communication, remains inaccessible to unauthorized individuals. We're just protecting our stuff, right? We're using encryption so that if someone's doing a packet capture, they can't just read plain text what we're sending. We also use it for authentication. So in the case of asymmetric encryption, the use of private keys for decryption proves the identity of the user, serving as a form of authentication. We're going to learn about how those key pairs, when we use public and private keys, do deliver authentication, especially when we use them for something like digital signatures. What else can encryption provide us? It can provide us with non-repudiation. So again, kind of tying back in to those digital signatures, they use asymmetric encryption to ensure that the sender cannot deny the authenticity of their sent message, okay? So non-repudiation ensures that the person, the sender, is who they say they are, and that nothing has been changed in transit, okay? Or excuse me, just that it just confirms that the sender is who they say they are. Another thing it provides us is compliance in some of our key industries. So many industries have regulations or even laws. So we think of laws, think of GDPR, HIPAA, sector regulations. You can think of like PCI DSS or NIST standards, right, when you're working in the government, that require the encryption of sensitive data to protect consumer privacy. So I come from a government background, so I don't know what level of encryption HIPAA requires, but I know for some NIST standards, the National Institute of Standards and Technologies, when you want to like have a secure enclave on the government system, like let's say a secret or TS network, just a small example is your RSA keys have to have a certain bit key length, right? So encryption also keeps us compliant depending on what industry that our company is involved with. So some key points to think about when we talk about encryption is the future of encryption. So encryption algorithms right now are pretty secure when we use like AES 256, but as we go into the future with like quantum computing, there's going to be an evolving landscape of cyber threats that could potentially do decryption on some of our most secure encryption algorithms we have now. Okay, next we're going to go over our first type of encryption, which is going to be symmetric encryption. So in symmetric encryption, the same key is used for both encryption and decryption. So when I want to turn my plain text into ciphertext, let's say I'm using a symmetric algorithm like AES. This is a symmetric block cipher algorithm or encryption standard. I'm going to use the same secret key that I generate when using AES. So to decrypt, right, if I'm the sender, let's say I'm Bob. If I want to encrypt using symmetric encryption or key algorithms, I create my key, and that key I'll have to send to the receiver, Alice over here, if she wants to decrypt the message I'm sending her. So what do we already see the problem with this, right? If we have to send this key, and that key is how we could potentially get compromised, right? Because in the wrong hands, now someone can perform that packet capture and see into our ciphertext by converting that ciphertext back into plain text. Because that actual algorithm is open standard, right? Anyone can use AES or any hardware vendors or software vendors. What keeps that secure is the secret random generated key there, okay? So just something to think about with symmetric encryption. So a use case for it, where do we typically use it? So this is often used for encrypting large amounts of data, such as databases, database information, or files on a disk. Okay, let me make sure I hit everything. Let's move on. So now we're going to go over the process of symmetric encryption. So let's say Amanda here, this is going to be the sender, wants to send Steven a message. So we have this plain text message. What she's going to do is generate a key for whatever encryption algorithm she's going to use. Let's say she's using something like AES. So she generates her secret key. Next, we're going to actually apply that algorithm using this generated secret key to that message. And now it's in ciphertext. We're then going to send that encrypted message over to the receiver, which is Steven. And then Steven's going to have to use Amanda's secret key to actually decrypt that information. And then once he does that, now he can see that plain text message. So again, what do we see here that could potentially be the issue? It's that key exchange process. How do we securely send that key over to the receiver? Like, we can't encrypt our own secret key, right? So how do we accomplish that? How do we securely do key exchange? And we want to be able to use symmetric encryption, right? Because it's a lot faster and it doesn't take as much computational overhead as like an asymmetric encryption would use. So like when we do like TLS encryption, that cipher suite uses a stream cipher symmetric encryption algorithms like Cha-Cha or Salsa, right? You want to use that when it's a lot of data you need to encrypt, okay? So we still want to use symmetric encryption algorithms. The reason I say that is because a lot of my students are like, well, why even use it if it's not secure, if that key could get compromised when you have to send it out of band, right? Or you have to send it in a secure fashion. How is it even possible? Well, the way we do secure key exchange is through asymmetric encryption. So our asymmetric encryption enables us to create a unique shared secret key between sender and receiver for symmetric encryption. So let's go over that. So asymmetric encryption, also known as public key cryptography, it involves two keys, a public key and a private key. So when we do asymmetric encryption, and let's say we have to generate, for example, RSA keys, which is an asymmetric encryption algorithm. So you generate two keys, maybe on the CLI, you run a playbook or a runbook. When those keys are computed and made, it's just randomly designated public or private, meaning that those keys are just mathematically related, and then you choose which one's private and which one's going to be public for the rest of the world to be shared with, okay? So essentially what we're saying here is, let's say this user, when they create that public key and that private key, they're just arbitrarily chosen, okay? It's just two keys that are used to encrypt and decrypt and that are mathematically related, okay? So some example algorithms, we have RSA, we have ECC, elliptic curve cryptography, which is how we actually do secure key exchange. Also missing from this list is Diffie-Hellman, which we're going to get into. So asymmetric encryption. This is commonly used for secure key exchange, also putting digital signatures on messages, and encrypting small pieces of data like maybe some passwords, okay? Now, let's get into the flow of asymmetric encryption. If we want to send information using asymmetric encryption, how do we do it? Okay, so first off, we have the sender and the receiver here. So Amanda now is going to use asymmetric encryption to send Steven a message. So we want to encrypt that plain text message here. So what's going to happen is that both users are going to have to generate their key pairs. And then that public key is going to be shared within the organization or globally. So this is kind of why PKI is tied into this, because if you have enterprise PKI, every single user probably has public and private key pairs unique to them, and that public key pair can be published, right, out to the enterprise. So getting back, right, Amanda needs to send Steven an encrypted message using asymmetric encryption. So they both generate public-private key pairs. And remember, these are mathematically related to each other, and it's arbitrary which one we designate as public or private. Next, what Amanda's going to do is she is going to take the receiver's public key, so Steven's public key, and encrypt it. So we're encrypting using Steven's public key, right? Which again is global for anyone. So you may be wondering, well, how is it secure? Well, because the only thing that can decrypt the public key is the user's private key. And that private key is going nowhere. It's supposed to be stored locally on that laptop, or maybe in a secure enclave or a hardware security module that's local and secure to that enterprise, okay? So the only thing that can decrypt the public key is the user's private key, which should have been generated with that key, okay? Because remember, they're mathematically related. So once we send that encrypted message over from sender to receiver, the receiver is going to receive that encrypted message, like, okay, well, I'm getting it in ciphertext. Well, only thing I have to decrypt is my private key. So I'm going to do that. So if that private key is able to decrypt, that means his public key was used to encrypt. So now we get that plain text message. Okay, so now that we have learned asymmetric encryption algorithms and cryptography, we know that there's a huge computational overhead with asymmetric encryption. We don't use it for like data in transit. We don't even use it to encrypt data at rest, like with full disk encryption. We use symmetric. So how can we, let's say if we go back a slide, be able to have this constant communication using symmetric encryption after this has already been done? What can we do? Well, due to a very confusing math and something called the Diffie-Hellman key exchange, we're able to do that. So as you see here, Alice and Bob, they have their private keys. What they're going to do is send each other their public keys, and then using this algorithm here, whatever that math means, so using Alice's private key and Bob's public key, they're going to add these two together to create this single key. And then Bob is going to do the same thing. He's going to use his private key and combine it with Alice's public key to create a single shared key. And through the wizardry of the Diffie-Hellman algorithm and key exchange, now those two keys are mathematically related. And even if it's like stolen in transit, it doesn't matter, right? Because another user cannot recreate this. You need these two exchanging their public keys with each other to create that individual shared secret key. So this is a way we get symmetric encryption, right? Through the use of asymmetry. Because asymmetry, we have these key pairs that are then going to be exchanged with each other, the public ones, to combine it with their own personal private key to create that shared secret key. Another way to do this, instead of using these, because if you look back here, essentially we're using large prime numbers, not to get too deep into the actual algorithm, but we're using prime numbers to do Diffie-Hellman, okay? With elliptic curve cryptography, we're doing the same thing. We're just doing asymmetry to create a shared symmetric key, but instead of using prime numbers, we're using curves, okay? So these curves will determine will be in place of our large prime numbers that are used in Diffie-Hellman key exchange. Okay, so just to cap it all off, right? So in both Diffie-Hellman and ECC, the shared secret key derived from these exchanges is typically used to encrypt further communication using symmetric encryption. So let's say we use like Diffie-Hellman to do key exchange. After we've done that, we can use something like AES to encrypt our data in transit using that shared secret key, okay? So this approach combines the security of asymmetric encryption for key exchange with the efficiency of symmetric encryption for data transfer. So some security implications. So with Diffie-Hellman, while secure, its main vulnerability lies in the possibility of a man-in-the-middle attack if the initial public key exchange is not authenticated. So essentially that just means if someone's doing a packet capture in the middle and takes that public key, they can be part of that shared secret key, right, mathematically. ECC offers high security with shorter key lengths, but requires careful implementation to avoid vulnerabilities. Essentially just saying it's a little bit harder for computers to compute those curves rather than just large prime numbers, even though those curves end up equaling a number, right? And then something they both provide is forward secrecy, meaning that if a private key is compromised in the future, past encryption encrypted with the derived shared keys remains secure, okay? So let's say we had a secure session. We securely did key exchange using Diffie-Hellman. So we created that shared secret key between each other. I know my drawings are really bad. If that key gets, like, let's say our session, boom, and then it ends. And let's say someone stole that key and tries to recreate that session. It isn't going to work, okay? So now let's go over some of the different algorithms. So triple DES, this is a symmetric encryption algorithm. So this is kind of not used anymore. It's a block cipher, that uses 2 or 3 unique keys that increases the bit key length from regular DES, but it has slower performance compared to AES. We also have RC4, another symmetric encryption algorithm. So RC4 is a stream cipher that's going to generate a pseudo-random stream of bits, key stream, and then for encryption, the key stream is combined with the plain text using the bitwise XOR operation. So essentially, that's kind of giving us like an initialization vector to keep unique encryption on all of our bits. And it supports keys ranging from 40 to 2048 bits. So RC4 now is vulnerable. So it's largely replaced with AES. And then, of course, I don't have an AES in there. Okay. Now, asymmetric encryption algorithms, we have our RSA. That's a very common one. So RSA algorithm is based on the mathematical difficulty of factoring the product of 2 large prime numbers. So with RSA, that we do key generation. So we do have a public and private key. And RSA is widely used for secure data transmission, digital signatures, and key exchange mechanisms and protocols like TLS. Another big one, right, is SSH. And if you come from a networking background like I do, when we configure SSH on our network, we have to create RSA public and private key pairs, right? And since I don't have a slide on it, apparently, I want to talk about AES. This stands for the Advanced Encryption Standard. So this is our modern symmetric encryption algorithm. It's going to be used for pretty much everything, right? IPsec, TLS, all use AES encryption, or they can use AES encryption. And it comes in 3 major bit key lengths. So it's going to be 128, 192, and 256. And this is going to be the standard. So even in like our enterprise communications, like our wireless networks, we use AES, like in WPA3. So that's going to be the most common encryption standard that you see out there. All right, so we're going to go ahead and stop this video. And on our next video, we're going to get into the different levels of encryption. So what we're talking about here is essentially how we apply encryption, right? To a disk, to a volume, to a database, etc. So what we're going to do now is we are going to pause the video. And then when we transition back in, we're going to do a quick quiz on symmetric and asymmetric encryption. All right, so now let's go over some questions going over cryptographic solutions and specifically encryption algorithms. So every single video, we're going to end it by going over these quiz questions, kind of just to reaffirm what we have learned. On our Academy site, whether you take our self-paced or our live virtual training, you get access to this practice exam software with over 1,000 questions, and each lesson will have a quiz at the end of it. So let's go ahead and get started. So I'm going to say the question, I'm going to take a little break, let you pause the video, answer, and then we'll go ahead and answer together and look at the explanation. So question 1, what is symmetric encryption? So A is encryption where the same keys used for both encryption and decryption. B, encryption where different keys are used. C, a type of encryption that doesn't require a key. I'm going to go with A here before even getting to the rest of the answers. And you can see here the explanation tells us yes, we're right, and that is the correct answer. Question 2, what is asymmetric encryption? So the answer here is going to be A method using different keys for encryption and decryption where one is public and the other is private. Let's go ahead and submit that answer. And look at that, we're right. A, asymmetric encryption, also known as public key cryptography, uses a pair of keys, a public and a private key. Next question. Which of the following is a common use of asymmetric encryption? A is encrypting data stored on a hard drive. B, encrypting data in transit. C, compressing data. Or D, speeding up the data transfer over the internet. I'm going to go with B, encrypting data in transit like secure web communications, and that is correct. So using HTTPS, TLS, you use asymmetric encryption to make that initial connection to the web server. That's part of the public key infrastructure, which we're going to go over in the next couple videos. Then last question, what is encryption? So here I'm going to answer the wrong I'm going to answer incorrectly just to show you how our software works, giving you the correct answer in the explanation below. So I'm going to go with C, a technique for speeding up computer performance. And we know that's not true, right? We know it's B, secure communications, okay? So here, even though we get it wrong, it tells us what the correct answer is and also an explanation down below as well. All right, I want to thank everyone for viewing. And please feel free to like and subscribe. And if you're an active duty, reserve, or National Guard soldier, click that link in the description below to learn how you can use your benefits up to $4,000 a year for any credentialing or certification assistance. That's right. You could get all your training for free. You get access to our Academy site with over 1,000 practice questions and a voucher for free using your benefits. Click that link below to see how you can, if you qualify, and how you can apply. And I want to thank again everyone for viewing.